Hi, and welcome back to the Physics 102 challenge videos here at McGill. I'm Matthew Heffernan, and this week we're going to be going through a problem we actually did in class, but may need some extra review. So what I have set up here is a circuit, and it involves a buzzer. So first I'll begin by sort of laying out the problem here. So a buzzer can be made of piezoelectric material that can be made to vibrate by expanding or contracting when an electric charge is applied to it. So when you discharge a capacitor. And the kind of place we see this is in things like cell phones when they vibrate. So bzz, bzz, that's the exact sort of thing we're going for. So we include a special switch here from A to B that closes when the voltage drop across it is 5 volts and opens when the voltage drop is 1.85 volts. So the voltage that this will create is a sawtooth. So the question is, we want to find the capacitance C in the circuit that makes the material vibrate at 10 hertz. So first let's begin by writing it down. F equals 10 hertz. Okay. So what this does here is it will switch us from charging the capacitor to discharging the capacitor. So when that's open, the current was going to go from the battery to charging the capacitor, and it's going to go through the buzzer. So it's going to buzz. When it hits 5 volts, it's going to close, and the current is instead going to go through here, only focusing on this part of the circuit, discharging the capacitor. For the purposes of this problem, we're also only going to consider that the buzzer has effectively no resistance. Well, that might not be true in practice. For the purposes of our example, it's sufficient. Okay, so the first thing we're going to do is we're going to analyze that sawtooth. So the sawtooth pattern looks sort of like this. And we know that from here to here, since the frequency is 10 hertz, it's going to go in the period of 0.1 seconds. Okay, but what that tells us is that it discharges and then charges again in 0.1 seconds. So let's also fill out this diagram here a little bit. Let's have this as 1.85 volts and this as 5 volts. Now, for those who are a little bit more familiar with exponential decays, we know that 5 times 1 over e, where e is the natural number, is equal to 1.85, approximately. So this means that it drops to 1 over e of the value in one period, which is exactly what we're looking for. So that's why those numbers are chosen. So if we know that charges and discharges in a total of 0.1 seconds, then we know that the time constant, tau, should be 0.05 seconds. So half of that. So the time it takes to go from charged to discharged. Okay, let's add that to what we know over here. 0.05 seconds, and let's clear up some room. So one thing we're also going to note in this problem is there's a complicated resistor. So that's the Wheatstone bridge that we've already seen. But one thing we know, since we were watching the challenge video from last week, is that that's a balanced Wheatstone bridge. So this entire thing, the equivalent resistance of it, can be found, and in fact we've already found it. So, since we've already found it, let's just write down here, Req, for the equivalent resistance, is equal to 5.45 kiloohms. Okay. So we also know, for the time constant, tau is equal to Rc. Well, the R in this circuit is going to be the equivalent resistance of that resistor network, which we conveniently have already calculated. So we know that is equal to 5.45 kiloohms times C, which is equal to, of course, 0.05 seconds. So what that tells us is that this equivalent capacitance over here, CEQ, is going to be equal to 0.05 seconds divided by 5.45 kiloohms. So what we found here is we have 0.05 seconds divided by 5.45 kiloohms. Now let's get out our trusty calculators that we use all the time and divide 0.05 by 5450, which gives us 9.17 microfarads. Okay, so now we have a value that we need for CEQ. Let's write that over here. CEQ is equal to 9.17 microfarads. Okay. So we also know how to decompose that resistor, that capacitor network. We've done it in class this past week, and we can just break it down using the way we already know that capacitors add. So the first thing we see is that we have two branches, one on the left-hand side where there's two in series, and then the right-hand side, which is just that one. Okay, so what we know from that is that CEQ is just equal to 1.076 microfarads over here plus C over 2. Okay, but we know CEQ, so we know that 9.17 microfarads is equal to 1.076 microfarads plus C over 2. Okay, we subtract 1.076 microfarads from both sides and multiply by 2. So we have over here 9.17 minus 1.076, so that is 8.0, well actually it's going to be 7.9 something. So another lesson is when we have a calculator available, always use it. So let's take 9.17 divided by, minus 1.076, and we have 8.094 microfarads is equal to C over 2. Let's multiply by 2. So 8.094 times 2, 8.094 times 2 is equal, so C is equal to 16.188 microfarads. So now that will give us the characteristic sawtooth behavior we're looking for. We've solved this circuit so that it gives us a frequency of 10 Hertz, and this will in fact produce the buzzer that we're looking for. So next time your phone goes buzz, 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 assume there's a buzzer there, and if you really want, you can try to find out what is the time constant that would go into it, just for fun.